Hi, good morning. Today we are going to discuss one principle that is called Minimax Principle. Okay, and this is corollary 6.2.7. Fisher have proved this in the case of finite dimensional space, and Hilbert Curran proved this in the case of infinite dimensional Hilbert space. Now, just look at what was the statement of the minimax principle. Let lambda n plus 1 plus is greater than 0. What is the meaning of that? The positive eigenvalues lambda I plus are positive eigenvalues, and here our assumption is lambda n plus 1 plus is greater than 0. Okay, and that means the operator T has at least n plus 1 positive eigenvalues. Then the result says that lambda n plus 1 plus is equal to minimum of x1, x2, etc. xn, phi of x1, x2, etc. xn. Now what is phi of x1, x2, etc. xn? Phi of x1, x2, etc. xn is actually supremum of norm of x equal to 1 inner product of txx such that x is in the span of xi, I varies from 1 to n per. Okay, so we are collecting those x such that for such x, norm of x must be 1. Also, that x is orthogonal to span of x1, x2, etc. xn. So this means x is actually orthogonal to xi for every I equal to 1 to etc. n. So we are considering those x, listen carefully, we are considering those x such that x is orthogonal to span of x1, x2, etc. xn and norm of x equal to 1. And for such x, we are evaluating inner product of tx and x. Then we are taking supremum. So that supremum value is called phi of x1, x2, etc. xn. Clear? First we consider x1, x2, etc. xn in H. Okay. Then you choose x such that norm of x equal to 1 and x is orthogonal to span of x1, x2, etc. xn. Then evaluate inner product txx. Then take supremum. Okay, supremum over those x such that norm of x equal to 1. Okay, and that supremum value is known as phi of x1, x2, etc. xn. Okay, here span of x1, x2, etc. xn. So phi, what is phi of x1, x2, x3? Suppose this is equal to same supremum norm of x equal to 1. That's such that x belongs to span of x1, x2, x3 whole term. Okay, clear? So now, after evaluating each phi of x1, x2, etc., xn for each x1, x2, etc., xn. So, we are considering those n tuples. We are not saying tuple. Those x1, x2, etc., xn. And then evaluate. That is, we are choosing some x1, x2, etc., xn in H. Then evaluate phi of x1, x2, etc., xn for each n tuple. Okay. Then the minimum of those phi of x1, x2, etc. xn must be lambda n plus 1 plus. This is our result. Hope statement is clear. Okay. Now we will move to the proof. Listen carefully. So first we apply, okay, to prove the theorem. First we apply corollary 6.2.6 to the operator T restricted to span of x1, x2, etc. xn per. Just recall corollary 6.2.6. Okay. So here we are applying that to T restricted to span of x1, x2, etc. xn per. Okay. So just to look at this. We have one result. If L is a subspace of H, then L closure is, L complement is set of all those X belongs to H such that X is orthogonal to L. And it is a, L perp is a closed subspace of H. Okay. Therefore, span of x1, x2, etc. xn perp is a closed subspace of H. And closed subspace of a Hilbert space is always complete. Therefore, we can easily say we can easily say that the restriction function T restricted to span of x1, x2, etc. xn perp is also symmetric and compact linear operator. Okay. So, we can apply corollary 6.2.6 to T restricted to x1, x2, etc. xn per. Clear? Okay. Then, the next result is then lambda n plus 1 plus equal to maximum of txx, x is orthogonal to ei plus I varies from 1 to etc. n. Okay. Then lambda n plus 1 plus is this one. So now we will move to the proof of this result. Okay. No need to write this proof for exam. Just look at. Okay. By 6.2.6, lambda 1 plus equal to maximum of norm of x equal to 1 inner product of tx x if there exists a positive eigenvalue. In our assumption, lambda n plus 1 plus is greater than 0. Therefore, there exists at least n plus 1 positive eigenvalue. So, that means this result is true. Okay. So, we are applying. We have this result in the proofs. Just uh, see the proof of 6.2.6. Here we have Txx is less than or equal to sigma lambda I plus inner product of xei plus whole square. Now, if x is orthogonal to ei for every I equal to 1 to n, what about inner product of xei plus? That is equal to 0 for I equal to 1 to etc. n because x is orthogonal to ei plus. Now, what about inner product of txx? This is actually, if you assume this is some sigma I varies from 1 to this you can write as sigma I greater than or equal to n plus 1. Okay. And up to n, inner product xi ei plus is 0 inner product. Okay. So this term is actually equal to 0. We have inner product of xei plus is equal to 0 for I equal to 1 to n. Therefore, this is actually less than or equal to sigma I greater than or equal to, you can greater than or equal to n plus 1 lambda I plus inner product xei plus whole square. Okay. So, but what we have lambda 1 plus is greater than lambda 2 plus is greater than etc. That means lambda n plus 1 plus is greater than lambda n plus 2 plus etc. So you can replace lambda n plus 2 etc. by lambda n plus 1. Okay, so this is equal to, you can take lambda n plus 1 outside, then lambda n plus 1 plus sigma I greater than or equal to n plus 1 modulus of inner product of xei plus whole square. Okay, and this is less than or equal to norm of x square by Bessel's inequality. Okay, so for all x with the norm of x equal to 1, inner product of txx is less than or equal to lambda n plus 1 plus. Clear? Thus we have for every x with the norm of x equal to 1 and x is orthogonal to ei plus, then lambda x, inner product of tx x is less than or equal to lambda n plus 1 plus. Okay. So if we take x is equal to en plus plus, then what we will get? Inner product t en plus 1 en plus 1 plus is equal to lambda n plus 1 plus. Okay, just to go through proof of 6.2.6. Okay, thus we get inner product txx is equal to lambda n plus 1. This implies maximum of norm of x equal to 1. Inner product txx is equal to lambda n plus 1 plus. Okay, so what we have, x is orthogonal to ei plus for I equal to 1 to etc. And that means x is orthogonal to z for every z belongs to span of e1 plus etc. plus en plus. That means x belongs to span of e1, e2 etc. en plus perp. Okay. Therefore, you note that phi of x1, x2, etc. xn is supremum of norm of x such that this value. Okay. Here, x is in span of this perp. Okay. So, what is this actually? This is actually phi of e1 plus e2 plus etc. plus en plus. Just look at this. Phi of E1 plus E2 plus etc. plus En plus equal to supremum of norm of x equal to 1. Inner product Tx x such that x belongs to span of Ei plus I varies from 1 to etc. n. Okay. Therefore, we get phi of E1 plus E2 plus etc. plus En plus is equal to lambda n plus 1 plus. Okay. Thus we get phi of E1 plus E2 plus etc. plus En plus equal to lambda n plus plus. Now what we have to prove? Now just look at the statement of the theorem. Here we have to prove minimum of x1, x2, etc. xn phi of x1, x2, etc. xn equal to lambda n plus 1 plus. Okay. But now we get phi of E1 plus E2 plus etc. plus En plus is equal to lambda n plus 1 plus. So to prove the result, if we prove phi of x1, x2, etc. xn is greater than or equal to lambda n plus 1 plus for every x1, x2, etc. xn, then minimum of x1, x2, etc. xn is equal to xn in phi of x1, x2, etc. xn is equal to lambda n plus 1 plus. So if we prove, we have to prove this. If we prove this, then we get proof of our corollary. Okay, that is we have to prove phi of x1 because at the point e1 plus e2 plus etc. plus en plus the value is lambda n plus 1 plus. And minimum, if we prove phi of x1, x2, etc. xn is greater than or equal to lambda n plus 1 plus, then minimum value is equal to lambda n plus 1 plus, and e1 plus e2 plus etc. plus en plus uh, is a point at which minima attained. So our aim is to prove this. Phi of x1, x2, etc. xn is greater than or equal to lambda n plus 1 plus. Okay. So what is phi of x1, x2, etc. xn? By definition, phi of x1, x2, etc. xn is supremum of this. So to prove this, it is enough to prove supremum greater than or equal to lambda n plus 1 means actually we have to prove inner product tx greater than or equal to n plus 1. So it is enough to prove inner product txx greater than or equal to lambda n plus for every x belongs to span of x1, x2, etc. xn per with the norm of x equal to 1. Because if we prove this, that means supremum value is also greater than or equal to lambda n plus 1 plus. This implies phi of x1, x2, etc. xn is greater than or equal to lambda n plus 1 plus. Okay. So we are assuming one claim. Now what is that claim? There exists a y such that y is orthogonal to x1, x2, etc. xn and norm of y equal to 1. Also y belongs to span of e1 plus e2 plus etc. plus en plus. So this is our claim. So we have to, if we prove this claim, then we are through. Okay. So first we have to prove there exists a y with the norm of y equal to 1 and y is orthogonal to x1, x2, etc. xn. Also y belongs to span of x1, e1 plus e2 plus etc. plus en. So we have to find a y such that y is in span. That means y is linear combination of e1 plus e2 plus etc. plus en plus 1 plus. Okay. And we have to uh, find y such that y is orthogonal to this one. That is y inner product yx1 equal to 0, inner product yx2 equal to 0, etc. Inner product yxn equal to 0. Okay, so we have to find b1, b2, etc. bn plus 1 in such a way that inner product of this x1 equal to 0, inner product of this x2 equal to 0, etc. Inner product of this into y into xn is equal to 0. So what about the first inner product? This is b1 e1 plus b2 e2 plus etc. plus bn plus 1 en plus 1 comma x1. Using linearity property, we get b1 inner product e1 plus x1 plus b2 e2 plus x, etc. So we get a system of how many equations? x1, x2, etc. up to xn. And how many variables here? Here we have n variables. Okay. Sorry, here we have n plus 1 variables. N plus 1 variables b1, b2, etc. bn plus 1. And how many equations we have? N equations, x1, x2, etc. Okay. So we have n equations and the n plus 1 variables means, and the system is homogeneous. That means this system has a non-trivial solution. And let the solution be b1, b2, etc. bn plus 1. Okay. So now we are assuming b equal to norm of b1 square plus norm of b, sorry, modulus of b1 square plus modulus of b2 square plus etc. plus modulus of bn plus 1 square whole raised to 1 by 2. And set a1 equal to b1 by b, a2 equal to b2 by b, etc. an plus 1 equal to bn plus 1 by b. Then a1, a2, etc. an plus 1 is also non-trivial because bi's are non-trivial. And also it is a solution of the above system because just we are multiplying by 1 by b. Okay. Now what about mod a1 square plus mod a2 square plus etc. plus mod an plus 1 whole square? This is actually mod b square. Okay, b square by b square equal to 1. So a1, a2, etc. an is a trivial solution and it also satisfies this condition. Now take y equal to a1 e1 plus a2 e2 plus etc. plus an plus 1 en plus 1 plus 1 en plus 1 plus then norm of y square is inner product yy and this is equal to this one. Okay, you can evaluate this. Now norm of y square equal to 1 implies norm of y equal to 1. Thus we get a y such that y equal to 1 and y is in the span of e1 into etc. en plus en plus 1 plus and also norm of y, okay, y is orthogonal to each e's, okay, each x's. Here we choose y such that inner product of yx1 equal to 0, inner product of yx2 equal to 0, etc. Okay. So we are choosing a1, a2, etc. an such that inner product of yx1, etc. equal to 0. Okay. So this y satisfies all the conditions of the claim. Thus we proved the claim. Okay. Now we have to prove the theorem. Okay. So y orthogonal to xi means y belongs to y orthogonal to z and y is in span of x1, x2, etc. xn per. We have phi of x1 equal to this one and this is greater than or equal to supremum of this is greater than or equal to inner product txx for every x belongs to. This phi, what is phi of x1, x2, etc.? This is the supremum value. Therefore, this is always greater than or equal to inner product tx for every x in span of x1, x2, etc. xn plus xn conjugate and norm of x equal to 1. Okay. So here we are taking y, and phi of x1, x2, etc. xn is greater than or equal to ty y, because y satisfies all the condition. Now inner product tyy is equal to inner product of t, you replace y like this. Okay. Now T E1 plus you can write as lambda 1 plus E1 plus etc. Okay. And lambda 1 plus norm of modulus of A1 square etc. And lambda 1 plus is greater than lambda n plus 1 plus, then taking each lambda is we are replacing by lambda n plus 1 plus, and taking lambda n plus 1 plus outside we get this one, and this is equal to 1. Therefore, phi of x1, x2, etc. xn is greater than or equal to lambda n plus 1 plus. This implies minimum of phi of x1, x2, etc. xn is greater than or equal to lambda n plus 1 plus. From A and B, we get lambda n plus 1 equal to minimum of x1, x2, etc. xn, phi of x1, x2, etc. xn. Okay.